Hello everyone. Today I'm going to try to show you how you can use that wonderful set of 4 kinematic equations we derived in class to solve problems of uniformly accelerated motion. So much like we did in a previous worksheet when we used graphs, here we're going to try to solve similar problems but use equations instead. So those of you that like math ought to really like this approach. So we're going to do 2 examples today. The first one, how long must a runway be for a plane to reach a takeoff velocity of 75 meters per second if it can accelerate at 2.0 meters per second squared? Well, there's a lot of variables in uniformly accelerated motion and in those kinematic equations, and so we need a way to kind of organize things. And to me, the best way to do this is to ask yourself a couple of questions. First of all, what is it that you need to find? What is the problem asking us? It's asking us how long the runway has to be. So what does that mean? Well, that's a displacement. So that's what we need to find. The second question is, what are you given in the problem? So let's look at the numbers here. For the plane to reach a takeoff velocity of 75 meters per second. So this is the velocity of the plane. Now, got to be a little careful here. Is it the initial velocity that it starts with? Or is it the final velocity it ends with? Well, if it's the takeoff velocity, it's got to be the final velocity. It's important that we get that right because otherwise we put things in the wrong places in the equations. This last one's a little easier to do if it can accelerate at 2.0 meters per second squared, so that's the acceleration. By the way, remember that means that the plane will speed up 2.0 meters per second every second that goes by. It's how quickly the velocity is changing. Now, if you look at the 4 kinematic equations, every one of them has 4 variables. And so we need to have 3 knowns to find the one unknown. And unfortunately, at this point, we only have 2 things that we know. So this is typical of these kinds of problems. Sometimes you have to read into them a little bit. So think through the other variables and see if we can read in. And hopefully, if you've ever taken off on a plane, you know that the plane starts at one end of the runway at 0 velocity. So it would be a reasonable assumption here that the initial velocity is 0 meters per second while the final is 75 meters per second. Now, knowing these 3 things, final velocity, acceleration, and initial velocity, and needing to find the displacement, we need to look at our set of 4 kinematic equations and decide which one would be appropriate. I say it's the 4th equation. Why the 4th one? Well, notice here, we don't have time. And all 3 of the first equations have time as a factor. So the 4th one is the only equation that has everything we know, final velocity, initial velocity, acceleration, and the thing we're trying to find. So this shouldn't be just like a random thing to decide on your equation. If you write down what you're looking for, what you know in the problem, it should help you organize things. Now, as I mentioned in class, I like to work these problems symbolically. And so that means that before I throw numbers in, I want to solve for what I'm looking for. The one thing I will do before I actually solve is get rid of zeros because they just get in the way anyway. So here's the initial velocity is 0, so that means the initial velocity squared is 0. So that term drops out. Now we're trying to find the displacement, so we have to do one step of algebra here. To move the 2 times the acceleration, we have to divide. I also have this habit of putting what I'm solving for on the left. So technically, I employed the reflexive property of equality to flip the sides of the equation. So hopefully you have the algebra to do this. Now we can plug the numbers in. The final velocity is 75 meters per second. Don't lose the squared. Those tend to disappear from one step to the next. The acceleration is a positive 2.0 meters per second squared. Now, before we just calculate out the numbers, let's check out the units, because the units should give us something that would work for displacement. So let's see what we have here. We have a meter per second, which is squared, divided by a meter per second squared. That horizontal line means divided by. So, first of all, we could square the meters per second, gives us meters squared per second squared, over meters per second squared, and now we can do some cancellation. The meter on the bottom cancels out one of the meters on top. The per second squared on the bottom cancels out the per second squared on top. And notice what we're left with. We're left with meters. Well, if you look at the problem, we're trying to find a displacement, a change in position. and so we would measure it in meters. So this shows here that at least dimensionally we have the right algebra done here. And if we had multiplied by 2a instead of dividing by 2a, our units wouldn't have checked out. We wouldn't have gotten meters, and that should have told us that we had done something wrong. So, you can, if you have the extra time, you can work through the units and see whether the units match what you're actually trying to find. Now, the other thing we have to look at, 2 sig figs, 2 sig figs. The 2 doesn't count. It's part of the equation, so you don't look at that. That's an exact number. So the least number of sig figs is 2. So if we square the 75, divide by 4, we get to 2 sig figs, 1,400 meters. Now, technically, of course, in a real runway, they'd want to build in some safety factor. But if the runway is at least 1,400 meters long, in order to get to 75 meters per second from rest, accelerating at 2.0 meters per second squared, if your runway is at least 1,400 meters, you will make it and you will be able to take off the runway. And again, I want to go over the process here just very quickly. We asked ourselves, what is it the problem's asking us? It's asking for the displacement, how long the runway is. Second question, what do we know in the problem? Now, 2 of the things were fairly straightforward in that they were numbers in the problem. The third thing, we had to read into the problem, and that very often happens. Once we know those 4 things, we pick the equation we need, we do the algebra, and we plug our numbers in and solve. And if we're really good, we check our units. So here is example number 2. I live up in Fenton, and so every day I have to hop in my car and drive down US 23 to get to Heartland to teach you wonderful boys and girls. So, in this case, if I bring a lunch, sometimes I put the lunch on the back of my car in order to get in or to move something around. And in this case, I've forgotten my lunch on my car. So I get up to US 23 and I start to drive, and my lunch falls off my car, and it slides 75 meters down the highway. Friction slows my lunch at 6 meters per second squared. How the heck we measured that, I don't know, but it's one of the givens. This is a couple-part problem here. I want to know first, A, how fast was the car moving when the lunch fell? Now, I underline car here because you need to realize that this problem is a little weird in that the numbers we have in the problem tell us about the lunch. But the question asks about how fast the car was moving when the lunch fell. So, what do we need to find? Well, if you think through the motion of the lunch here, hopefully you can see that in order to figure out how fast the car was moving, we need to figure out the initial velocity of the lunch. Why? Because the initial velocity of the lunch when it fell off the car is how fast the car was moving. Those 2 things would be the same. So if we work backwards here, figure out the initial velocity of the lunch, that will be how fast the car was moving. Second question, what are we given in the problem? Well, let's go along the numbers here. US 23 is the name of the highway. 75 meters is how far my lunch slid. And that would be, of course, a displacement. So our displacement is 75 meters. Friction slows my lunch at 6 meters per second squared, so that is the acceleration. Now, much as we had a little problem in the first problem, we have one here. We only have 2 givens, and we need 3. So let's think about what we could read into the problem. Now, if friction is slowing the lunch, eventually what's going to happen to it? It's going to stop. So the thing we can read in, the final velocity is 0 meters per second. So we know these 3 things. We're looking for the initial velocity. Is there an equation that has those 4 and only those 4 things? Indeed there is. That would be, of course, equation number 4, the one we used previously. So I'm trying to find the initial velocity here. I'm trying to solve for this. First thing I'm going to do is put in the fact that the final velocity is 0, so that drops out. So now if I want to solve for the initial velocity, the first thing I have to do is move the 2a times the displacement to the other side by subtracting. It's hooked up by addition, so I do subtraction. And then I don't want to know the initial velocity squared. I want to know the initial velocity. So to get that, I take the square root of both sides. I also flip the sides, reflexive property of equality, because I like to have what I'm solving for on the left. So we find that in this case, the initial velocity of the lunch, and therefore the velocity of the car, is the square root of negative 2a times the displacement. So let's plug the numbers in. And I hope you notice we have a problem here. If we multiply this all out, we're going to get a negative number. And a negative under the square root becomes an imaginary number. And although I made this problem up, I would like it to have a real answer. So we have a problem here. And one of two things has happened. Either we've done some algebra wrong, or we've made an incorrect assumption over here. And by the way, when you get a negative you don't want, that's not an opportunity to just use an eraser and wipe it away. Right? You need to figure out where your mistake is. So, think about this. Where did we make a mistake? Our algebra looks pretty good. So is there something over here we might have missed? Indeed there is. Some of you might have caught it when I first put the number up there. Friction slows my lunch at 6 meters per second squared. Well, if I'm moving in the positive direction, 75 meters, and I'm slowing down, what direction must my acceleration act? Indeed. It must act in the opposite direction, and therefore it must be negative. I could have been nice and put that negative into the problem, but I did put it in there under context. So you have to think about these things. So changing the 6 to a negative 6, now the negatives cancel. Right? We'll get a positive number under the square root. So 6 times 75 is, let's see, 450 times 2 is 900. Square root of 900, 1 sig fig, by the way, because there's only 1 sig fig in 6, is 30 meters per second with no decimal point. The conversion, by the way, from meters per second to miles per hour is about 2.2. So if we take this and multiply it by 2.2, it's about 66 miles an hour. But of course, US 23 has a speed limit of 70, so I did not exceed the speed limit. Right? Now, you might wonder why, was I going that fast before the lunch fell off? Well, if you know my car, you know that there's a spoiler on the back, and so maybe it got caught on there. And it's not a completely unreasonable thing, right, to have this 30 meter per second initial velocity. By the way, units, meters times meters per second squared, give you meters squared per second squared, and then you have to take the square root. Just as you take the square root of the number, you have to take the square root of the units. And the square root of a meter squared per second squared is a meter per second, which are, of course, velocity units. Again, hopefully encouraging us that we had done our algebra correctly. Now, part B. How long did it take the lunch to stop? So, what are we trying to find? We're trying to find the time. What are we given in the problem? Well, we're given all the things we had before. The displacement is 75 meters. The acceleration is negative 6 meters per second squared. The final velocity is 0 meters per second. And the initial velocity is 30 meters per second. Now, ideally, when you're doing these problems, it's a good thing to try to not use what you just found. Because if you use what you found and you got part A wrong, you're going to get part B wrong. But unfortunately, in this case, there's no other way to do the problem. And in order to find the time, all three equations that have time also have the initial velocity in it. So we can't get away from using what we found. But again, you're going to notice on the next worksheet that when I try to do these problems, if at all possible, I try not to use in B what I found in A. So, knowing all of these things, we can really use equations 1, 2, or 3 to find the time. And personally, I find equation number 1 to be the simplest. The final velocity is 0, so we'll cancel it out. To solve for t, we need to move the VO to the other side by subtraction. And then we need to divide by the acceleration. Now, do you have to show every one of these steps? No. But it would be nice to show some of the steps, right? And write as many of them as you need to convince yourself that you're doing the correct algebra. Plug in our answers. One thing I think you ought to notice here, the negative 6 and the negative from the algebra cancel out. So we have a positive amount of time, which makes sense. Had we forgotten the negative again, like we did in the first part, we would have gotten a negative amount of time, which meant my lunch would have had to go backwards in time, which would have been a neat trick. So again, negatives aren't just a reason to erase. You have to make sure you have the right numbers and do the right algebra. Unit-wise, we have a meter per second divided by a meter per second squared. And dividing by a meter per second squared is, of course, the same as multiplying by the reciprocal, a second squared over a meter. So the second on the bottom cancels with one of the seconds on top. The meters cancel the meters, and we are left with seconds. Exactly the units we would hope for if we're doing a time. 30 over 6, I hope you can do in your head. There's only one sig fig in each case, so we need one sig fig in our answer. 30 over 6 would be 5 seconds. So it takes my lunch 5 seconds to slide down the road. And in fact, if you take out a stopwatch, fun with PowerPoint, my Mr. K lunchbox actually takes 5 seconds to stop. Oh, PowerPoint. It's a wonderful thing. So I hope this helped you understand how to use the kinematic equations to solve problems of uniformly accelerated motion. Have fun on the next worksheet.